Ladies and gentlemen, good afternoon. So we have now a lecture related to the aspect of the interface between nanotechnology and biomedicine. We know that the conference is also devoted to nanotechnology and biomedical engineering. And this lecture I would like to draw your attention to its importance for you, and actually the subject is important for all of us. It's intersection between higher technologies, nanotechnologies and biomedicine. And I am happy to have this possibility to introduce to you Professor Adelung, the author of the latest material in the world, graphite, that you succeeded to develop and to introduce and to publish. And so we enjoy this lecture, 1 hour lecture. So Professor Adelung just from the airport came directly to this room, and so I'm sure that all of us, you and me, and all of us will enjoy this lecture. So you have the floor, Professor.
Yeah, thank you very much for the kind invitation, and for bringing me here. And description was that I should talk a little bit about something which is connected between engineering, biomedical materials, and so on. So, well, I'm myself a physicist, and then I was kind of converted to an engineer after my PhD, and it turned out, even though I was working with semiconductor materials, that I bumped into this kind of biomedical field, and it was more and more important for me. So I brought some mix kind of out of some lecture slides I gave in the biomaterials lecture, and some of the discoveries which is done by my students in the group, and they could be used kind of at the interface. It's like also a commercial for interdisciplinary, so now the tendency is more and more that one is not staying so much in his kind of own world like electrical engineering or material science, but that everything is connected. And this has a reason. This is basically because of the nanoscale aspects. Nanotechnology brings it together. So there's a very rapid kind of introduction to nanotechnology. Probably I'm not telling anyone anything new. Then I want to come to some important aspects which I found as somebody who was only learning into that field very important, which is hydrophilicity and hydrophobicity, which is dictating quite a lot in terms of biomaterials. And then I want to talk a little bit about nanotechnology and concepts which are already established about drug delivery, and then some of these discoveries which caused me to go more in this field, that there's a kind of interaction between nanoscale semiconductors and viruses. So, let's start with nanotechnology. So, very soft introduction. Well, what's nanotechnology about? Basically about scale. So you have here structure size, you have typical objects in the structure size. So we are living somewhere here at the meter scale, and then there's a millimeter scale, there's a micrometer scale, and there's a nanometer scale. And if you see, and if you're kind of taking a look, also done by a Japanese group which could cross the scanning probe microscope with a transition electron microscope, and they pulled out a nanowire out of only 3 or 4 gold atoms. And so, of course, now the mechanisms completely change on the nanoscale compared to the macro scale. And this is what all these scales have in common. So down at the nanoscale, things run differently. We know this from very common definitions of nanotechnology. If you take just one definition like Wikipedia or something, then it's most of the time lengthy, it's not so compact. You're finding there's something about scales, so 1 to 100 nanometers, but there are other features connected with that. So there's some new things in it. For example, quantum mechanical effects dominate this, and there's always discussed kind of special properties of matter which you find at this state and which you have to consider. So basically, electrical conductive wire is not conducting that well anymore at the nanoscale, but therefore it has other very interesting features you can utilize quantum mechanically. So what's different at the nanoscale size below 100 nanometers roughly, and additional features like quantum mechanics or special properties like high surface to volume ratio. Those which are from electrical engineering know that it's a good idea if you're making a sensor that you take a nanowire because it has a high surface to volume ratio. Only the little absorption of gas atoms on the surface can alter the current inside significantly. This is an example from University of Kiel, which is also called Christian-Albrechts University. This is a guy who founded the university. Abbreviation is CAU. And nowadays it's no problem to control individual atoms and push them around. These are experiments demonstrated since 20 years. If you have a low temperature scanning probe microscope, you can push them in place. These are manganese atoms which are on a silver surface, and you can see here some kind of waves. Those are depicted here in this tunneling microscope by calculating the density of states of the electrons here by taking the derivative of the tunneling current, and you can see that there's an interaction of the free electrons of silver here with the manganese atoms. So those are typical quantum mechanical effects. Another aspect I want to emphasize on this kind of nanotechnology that meets basically biomedical aspects is it's at the scale of biomolecules. In a physics journal I copied this type of picture which shows the DNA going around a carbon nanotube. So both are at the same scale, and this brings you into a kind of whole new world. So somehow chemistry, physics and biology and medicine all come together, and now you can do some influence on these biomolecules with your structures if they are on the nanoscale. So there's a kind of important interplay. And as soon as the people realized that, then they had fantasies about nano robots, for example, machines going into the blood cycle and do there all kinds of things. So this sounds really like science fiction. And if you're starting from physics with ultra-high vacuum equipment and so on, you will see it's a very complicated. You can make some little tools, wheels and so on. But actually these nanorobots, in this sense, they exist, and they are here in the room and all of us. These are basically biological structures. If you're taking a look at biomolecules, they are often like these type of robots. So nature is kind of utilizing that. Since roughly 4 billion years, evolution created these type of allosteric molecules which can switch between different states, and they have even a kind of fuel, a kind of energy supply, which is called the adenosine triphosphate, which is such a molecule. And it can split off one of these groups, and then you win some energy, 32.3 kilojoule per mole, which is some energy like if we would burn fuel in your car. And this is what you win by splitting off one group here. And this is going to happen inside molecules which can change their morphology. And during that splitting, the energy is used to change this morphology. And this keeps it running. And I was very surprised when I was seeing this animation from Harvard University. Those who don't know that, I can really recommend it. If you want to get quickly into the field, somebody is obviously knowing this is the inner life of a cell. They took a lot of money in order to animate things which are going on in a cell. So they show on the molecular scale what is going on, if there's some inflammation reaction, and how all these tiny little molecules react on the surface. So I have a part of this movie in order to show you, and these guys in Harvard are really serious, so they're not doing science fiction, in order to show that this is really what is going on. So this is this movie, Inner Life of a Cell, from Harvard. You see it here directly from the website from Harvard. So if you search for Inner Life of a Cell and Harvard, you will find this movie. And I don't want to show the whole movie, this would be too long, but just some important aspects around here. So here's some polymerization and so on of these biomolecules, but what is most fantastic is this kind of transport mechanisms which are occurring. So this is now depolymerization. Inside of a cell everything is combined and taken into a part permanently. And against chemical gradients on these roads called microtubules, you can transport some chemistry against chemical gradients. And therefore you need these motor proteins which are basically switching between two states and are combined by biology to complicate machines. This is this funny guy here. You see here now two motor proteins where constantly this adenosine triphosphate is converted to adenosine diphosphate with every stroke it is doing. And there's a charge which gives direction, and this fits perfectly into each other. And there's some vesicles which are having inside some chemistry which is now transported up to the outside of the cell. So I hope this caught your attention for this topic. The rest you can see at home. As I said, it's Harvard University page. There are much more movies and explanations, and it's very nice to get fast into the field. So, yeah, this is what somehow evolution does. And so the question is, why can't we do that? Well, we are at the beginning now to understand these interactions, and we can at least on a tiny scale start to interact with this type of molecules. What do we need for that to understand? And as I mentioned at the very beginning, I think one very important topic is the wettability. So to understand this. So what is wettability? Sounds a bit boring, so it's like bringing kind of liquids which are polar, like water, somehow to surfaces. So now the lecture part comes, so I'm telling you about this kind of story a little bit. Hope that I'm telling you something new. And interconnected are kind of some questions from biological objects. So think of you would be, for example, a beetle, and you want to kind of survive in the desert and collect water. So with tricky hydrophobicity and hydrophilicity, you can do that. So there are some desert beetles which can do that. Or if you're a plant and yeah, there's some dirt on your surface that you want to clean, but you have no arms. So how to do this? Again, answer will be tune your hydrophobicity. Or I don't know if you've seen this, if a duck is kind of coming out of a river, it's immediately dry. So they can also do that. So answer is already given here, let nature control your surface wettability. So to understand these extreme cases of wettability, we have very quickly to take a look into wettability. So what's going on? Yeah, what do we need to understand? Something about interface energy, interface tension, surface tension, and contact angle. Let's start simple from a droplet. If you would be a water molecule happy inside a droplet, then you would feel some attractive forces from all the other water molecules which are around you. So as a water molecule, you are a dipole, H2O, and you're partially charged. Typically, the oxygen is so electronegative, it really likes also to be close to some other water molecules, close to the hydrogen bonds there, and so therefore it's trying to interconnect it to this outside world, so that there's a called water bridge existing, so that there's an attraction between the different water molecules. So all these water molecules inside of the droplet, think of this would be a droplet, they are fine. The losers are outside here. These guys are poor off. Why? Because half of the interaction is missing. So there's this interaction between the water molecules, but these guys, they're in a higher energetical state because they're not bound to half of the other molecules. So those guys, if they would sink in, they would win a lot of energy by binding to all these other guys. So what is going on if you're at the International Space Station and it's boring and you have a bottle of water? So if you push a droplet out, it's always perfectly round. Why? Because surface to volume ratio, minimal surface, maximum of molecules inside. So, pretty simple so far. What is going on if you're now bothering your water droplet with some surface? So classical surface here, for example, could be a glass surface. You can make this experiment if it's raining and you're driving with your car, so you see all these droplets falling down on your windscreen, and they do not stay roundish, and that's not so nice. If they would stay roundish and roll off, you would not need windscreen wipers, and you would not need to renew them, and this is a different story. But at least this droplet is spreading to some point. Why is it spreading? Well, the situation gets slightly more complicated. You have your liquid-gas interface, you have here your solid-gas interface, not so important, and you have your solid-liquid interface. And if you're a water molecule here, and this material is really friendly to you, meaning that it's also quite polar, so you can, as a dipole, dock there quite nicely, and gain some energy, for example Coulomb energy. So if this is a metal, for example, there's free charge, and you can arrange things that you're also quite happy if you're sitting there. You might be even more happy to sit here at the interface than sitting here in the middle. And if you're more happy to sit at the interface, now you're a winner. So these are the losers kind of, and these are the winners, because they are tighter bound than the others. So how far can it go? As the droplet is still kind of intact, it kind of bends the droplet a little bit wider and wider, but while it's doing that, it kind of expands here this surface. And in this way, you have to invest somehow energy and bring more and more guys here to the surface, which are in an unfavorable state, in order to get more favorable. And there will be somewhere an equilibrium where you have these kind of molecules on top and molecules at the bottom. And now it simply says how attractive the surface is, how far the whole thing spreads. If it's very attractive, it spreads quite far, so invest a lot of energy here to the surface. If not, if it's more hydrophobic, one says, then there's only a tiny fraction kind of wetted. Yeah, energy-wise, I think I skip here the details. It's very simple. So the energy win or loss you get is somehow connected with the surface area you're creating. For example, if you bring up more water molecules to the surface, to this free surface on top, then you have to invest some energy. And this gamma is simply a constant, which is saying you something about the material's properties. So if you're at the interface between the droplet and the surface, then it says you, if it's attractive, then it gives you a lot of energy, so then it's a larger number, how it's bound. If you're talking about free surfaces with gas, then this is the surface tension, and this is describing how attractive the liquid itself is. There are liquids like water, which are polar, which have this hydrogen bridge mechanism thing where they all adhere together, but there are also liquids, for example typical solvents, which do not stay that tight together. Or more extreme, if you're thinking of liquid metals, think of mercury, then you have a very high surface tension, and therefore this is a quite high surface surface energy. You see this here. Mercury has here a high value compared to water. Acetone has a very low value compared to water. Okay, these are the basics. I don't want to bore you too much with all that stuff. How does it now come mathematically that you have now your water droplet here on the surface? There's a connection between the surface property, how much it's attracting the water, and the area here of the droplet. So the droplet spreads more if it's more attractive for the water, and the other way around, it will spread less if it's less attractive to water. So there's a quantity which you can easily measure called contact angle. This is shown here, theta. This contact angle says something about how nice it is for the water to wetten the surface. So if this contact angle is quite low, then it might be quite an attractive surface for the water because it spreads quite large and the angle is therefore low. If the angle is high, then it's not a very attractive surface, so then there's only a tiny fraction of surface attached to the water or coated with the water. There's this so-called Young equation which you can derive, which is telling you something about the wettability. This is giving you the connection between theta, this contact angle, and the wettability. This can be derived fairly easy. There's some derivation where you use some energies. This is discussed in the literature as being wrong. The more correct one seems to be here with some variation theory, where you're taking this surface and interface energies and count this together and ask yourself if this would be a droplet, a part of a droplet, magnified now, where you see here only the contact angle. If this guy spreads now a little, so would kind of wetten this surface further, how the whole energy balance is. And basically one can calculate it, you're gaining this kind of additional interface here, and you're gaining some, you have to invest into some more free energy, and in this way you're getting this first part here, where you're having a kind of this difference, where you have the solid gas interface and the solid liquid interface. So here you're losing solid liquid, you're losing solid gas interface, and you're winning solid liquid interface if you go here. And then you have your factor which says something about the attraction to this surface. And then if this is delta x, kind of the variation, it must be multiplied by delta x. And C is this, sorry, I'm telling wrong. This was the surface, and then C is the circumference in order to get an area. So you have here area, you have here your material constants, and you have here your energy. So now it's getting right. And here you have an additional term from the liquid gas interface. This is this additional interface you get here in order to consider this additional energy. Yeah, circumference of the droplet, and then times dx gives you this additional area. Yeah, so it's here and there this additional surface. And all you need now to do is to divide the whole thing by the area. Then you get the equation modified from here to here. And now you can say if nothing is going to happen and everything is in equilibrium, then you don't have a change of the surface area per energy. So this is 0. So basically this is 0. And then you're getting this Young-Laplace equation, which gives you a connection between this contact angle and this surface and interface energies. Yeah, maybe it's a long day for all of us, so I will reduce maybe the mathematics drastically and try to go more to the phenomena. If nobody objects. I don't know if there's additional questions. Please hesitate. I found this quite elegant. I found this in a book. It's much faster than all others. Okay, maybe this is because of my background as physicist. What do we need to know? This is approximately contact angle 120 degrees. So this is a photograph of a droplet on a surface just taken from the side. Typical contact angle experiment. And this is a maximum you can get with real world materials. Actually the polymers, Teflon, so PTFE, or silicone, PDMS, these are the most hydrophobic materials. So you cannot get anything more hydrophobic on a flat surface. Typically, if material is below 90 degrees, then it's hydrophilic. You can make the situation more complicated, so you can now evaluate some advancing and receding contact angles. what is more of importance is if you consider, and this is now bringing us back to the biomaterials aspects, what is going on if you're making the surface rough. And there were very early some discussions about this. You see this 1936 and 1944, and people had different models how now this interface here is changing. And in the Casey Baxter model, you see that this droplet is basically levitating over the surface, and here's some kind of still liquid gas interface, and here you have this additional solid liquid interface, and you have a mixture, and this is now changing the contact angle. To make a long story short, this allows you to go over these 120 degrees I was calling. So this allows you to make the droplet more roundish, and it could be quite interesting to have a droplet completely roundish, because then it would not wet the surface, but it would kind of slide almost frictionless over the surface. And you're not interested where these models have the kind of where they meet. Very simple access to this kind of effect, which is called superhydrophobicity, where a droplet is kind of roundish on the surface, can be gained by taking a look at capillaries. You all know what happens if you have a small capillary and dip this into some water. So the water level is rising to a certain point. If the capillary is more narrow, it's rising further. And there's a formula which tells you how far it goes. And the basic trick is, if this is wettening here the walls of the capillary, there's kind of no energy penalty. If you're wettening as a free droplet the surface, then you have to invest into a new kind of interface. But with the capillary situation here, if this one is rising, you have only winning here this eventually nice energy from wettening this new surface, but on top here, this free surface, this stays the same. So the only thing which stops it from wettening the capillary is gravity. So therefore there's a gravitational constant in that equation. So a tree can soak automatically with these capillaries water from the ground. What is typically not so much discussed is the anti-capillary effect, or the capillary depression. This is if you have now an unattractive material you're dipping into a water, because then the water level will not stay like here, but the water is pulled out, simply because of this energy balance again. So it's not very favorable to split this kind of water-water bonds you have in your liquid and wetten the surface. It's nicer to have this attraction from the other water molecules, so it stays below. Again, only the gravitation force that is in to that point. If there would be no gravitation, it would not even enter here at all. And the same is going on here. So now, how you can model a super hydrophobic surface, so a surface where droplets are almost roundish, well, you can think of you're turning these capillaries around and putting the water now on top and making a surface rough like this. So then the water droplet should penetrate here all these little channels, which is not energetically favorable. It's very unfavorable to penetrate here this different all this area, all these capillaries. And on the opposite, if you have an attractive surface, and this one is rough, then you have a so-called superhydrophilic situation. Then if you put a water droplet on it, it spreads further and further, because it can only gain energy to wetten all these little capillaries. And then it's kind of basically soaking the water completely inside. And nature is utilizing these concepts very often. So if you're taking, for example, a microscopy image from a plant, often plants have a specially designed superhydrophobic surface. So this microscope image, here you see this is 10 micrometers only. This one has 2 roughness scales. One are these bumps, and the others are even smaller. You can just only see this here on the surface. There is some tiny wax crystals which give another roughness scale. So all the surface is now this like capillaries, but not soaking capillaries, but rejecting capillaries. So these are all capillaries where it's not possible to bring in water because it's repelling the water. Here you can see a microscope image where you see a droplet, how this droplet is now behaving on the surface. So it's basically roundish, and on these capillaries, if you would press now this droplet with some force down here, then it would be very difficult to penetrate into this capillary. It costs a lot of energy. So therefore it would afterwards, after you're pressing it, go immediately back to this energetical favorable state. And this is kind of answering our first kind of question. If you're a plant and you want to clean yourself but you have no arms, then you let rain do the thing. It's called also lotus effect. So self-cleaning of biological surfaces. If this is a surface as schematic and you have a contact angle like this, which is almost 180 degrees, where the droplet rolls easily off, then this droplet is coming to the surface, and now it's rolling over the surface. And if there's some dirt on it, depicted here, it's immediately soaked in the droplet, because typically the droplet is wetting this dirt much better than the plant, and this dirt is staying on all these kind of little connectors. There's these 2 roughness scales, so it's not very well attached. And so then it will incorporate all these particles and then fall off. Of course, this holds only true if this is not ultra-hydrophobic dirt. For ultra-hydrophobic dirt, that's more special. So this is how this lotus effect is working. This works very well. I said I'm a physicist, so I tried to grow some plant on my office, and this is a result. This is obviously not alive anymore, but if we saw that what I told you, this is a surface of a plant which is basically equipped with these 2 roughness scales and these wax crystals. It doesn't have to be alive. So this works always. And if we are taking now, for example, a leaf from that here, and if you're putting now some water on top, it's ultra-hydrophobic, and it's difficult to see, of course, because I have now to balance it. You can see that the water droplet, I don't know if you can see it, I pass it around in a second so you can make yourself wet. It's kind of rolling easily around because it's basically frictionless, and it still works. Plant doesn't have to be alive for that. There's even a more extreme effect. So what if you're now trying to force this water to go to the surface, for example by shooting a water jet to this? Well, the energy of the water jet will, it will basically go on it if it's not cutting through. It will expand the circular cross-section of the water jet. It will expand it on the surface, and then it's creating a lot of free surface, which is energetically unfavorable. So it goes till all this kinetic energy kind of coming from the top is kind of in this expansion. Well, in the next state it's kind of going, if I take this angle, it's going forward, then it will repel, it will retract again, and it will overshoot. And because energy conservation and friction inside of water is absolutely negligible. So then it will push itself off from the surface, and there will be a water jet reflection, which is bad for you, because if I do that now, there will be water jet reflection. Here's something which I can flatten without making too much trouble. Okay, I try to shoot at my box in order to demonstrate you this. You see it's freely coming off the surface, and bouncing back. This is unnatural, so you can try to take all kind of surfaces, artificial surfaces, and put some water jet against it. You will see it typically never bounces off like this. It just goes and flows over the surface. But here it's ultra hydrophobic, so it's directly going off. I don't know if you can see here this type of movement. So this is now some mess. This concept is often used in nature. Maybe I can pass it around during that time so you have something to play, or I bore you with more examples. Nature is taking very clever. For example, this is a swimming fern. The swimming fern is called not diving fern, but swimming fern, because it wants to stay at the surface of the water. So the concept is clever. The surface is ultra hydrophobic. So there is a kind of wax capillaries which remove the water. While at the opposite side, it's hydrophilic. So it's attracting water very much. It's soaking it in. There's these anticapillaries. So if you have this type of ferns and there is some distortion in the water, so typically I bring some of those plants with me. Unfortunately, I don't have them here. You can shake, for example, a little glass with water with these ferns, like mad, and then in the next seconds they are at the right orientation directly at the surface, because one side is hydrophilic, this bottom side, and the other one is hydrophobic. So during rain, this fern will also stay alive and stay always on the water. The other principle runs as well. So this is a water strider. A water strider has very surprising legs. These legs are all equipped with these anticapillaries, or this capillary depression. So a water strider can run over the pond. And this is not one water strider, actually these are two water striders. I guess they want to demonstrate how good these legs are floating, because you can see now these dimples of the legs of the lower water strider, where the additional weight is on top, and you can see it cannot sink in. Researchers, yeah, they're doing scientific experiment, biological nature, I guess. So the those legs cannot penetrate. You have to push them very deep down into the water. Same effect here with our dead plant. It's the same. So maybe I can use this type of water now for that experiment. It works also with not distilled water. Not all water is distilled in nature. So you can also now try to, for example, put this down here underwater, and this will not work because it's ultra hydrophobic, of course. And you can feel here even the surface tension. And now I try to force it by pushing it from this area on, and you see it withstands. I cannot push it and penetrate it inside of the water. So nature is doing this in a quite clever manner, that it's not possible. Some of you have your own water. I could put that. You can maybe also play with that. It's interesting if you hold it at the outer part, then you can even feel kind of the surface tension because it's repulsion. And yeah, so these water striders are taking this. So what was with this desert beetle? Well, the desert beetle is simply playing ultra-hydrophobicity and ultra-hydrophilicity on its back. It has some ultra-hydrophilic parts where water is collected, and it lives in the Namib desert, and in this Namib desert there's in the morning some fog going on, and this fog is then collected at this hydrophilic parts. And these hydrophilic parts are only limited areas. Why is there an hydrophobic area? Wouldn't it be better to put it on hydrophobic areas? No, it wouldn't be better, because you you also want to harvest this water which is coming down here. So if there's a stream going down, some fog is going down through that, then more and more water is kind of collected on the hydrophilic parts. And if this part is touching the hydrophobic part, then the water droplet gets roundish. If the water droplet gets now bigger and bigger, and the water droplet itself is also absorbing water, then there's a certain point where it rolls off, and it rolls right in the neck of the beetle in order to be collected there. So it has like a water collection device there. And there's even, so this was also a report, I think, in Nature. If it's of interest, I can give you the slides for having these links for this beetle. Where one is using this technologically in order to collect this morning fog in an efficient manner. So it can do it more efficient than just with this hydrophilic concept. Question is, or I mentioned I'm a material scientist now, I want to make those structures also artificially. It's very easy because we know what we need to do. We need to have some kind of capillary type of surface, and we need to tune the surface energy. If we make it slightly hydrophilic and we would drill a lot of holes into the surface, then we would get the whole thing ultra hydrophilic, so extremely water absorbing. If we would go the other direction, if we make it hydrophobic from the energy, so only low energy facets, not very attractive, then it would be the other way around. And I have two students I was saying, one is actually a postdoctoral and the other is a doctoral student, which have shown that you can make even aluminum ultra hydrophobic. So I'm coming from University of Kiel, which is close to the Baltic Sea, so ships are quite of interest there. And so we took some ship aluminum, ALMG3, which is an aluminum alloy, and these guys are etching it in such a manner, you can see it here in the magnification, that you have only those crystalline facets which are low energetic. And I have here some of those here, some kept dry. So this is just normal aluminum surface, but one can see already it's not reflecting, that it's not so shiny on the surface, because the first 20 to 40 micrometers are structures like this. And now I'm out of toys. Ah, perfect. Okay. Okay. One can even see here that this aluminum has a tendency to be ultra hydrophobic. So you can see that water cannot stay here. It even shows this water jet reflection. So I better clean up here to look at the mess, otherwise I will be thrown out before giving the first lecture. What is this useful for? Okay, this is material science, it's immediately clear. If you want to have something corrosion resistant, kind of the best thing would be if the water would not even hit the surface. So with these anti-capillaries, you can do that. So why can they do this, and what is different from all other kind of techniques they're doing? Well, in my group, I'm successor from Professor Helmut Völl, who was here in a kind of long series of events. He's retired now, and this Dr. Carstensen and Mark Daniel Gallenbrust, they were in his group, and I took them to continue their work. There's a PhD student, and these two guys here, they're experts in semiconductor etching. This stuff here is a silicon wafer which is etched in a tricky manner, which has nothing to do with materials, but this is a very good battery anode, also hot topic. They know everything how to etch semiconductors. So these two guys said, well, we can etch perfectly semiconductors, let's etch metals now like a semiconductor. So what they're doing is they're making a very thin oxide film on top, like on the aluminum, and then they're etching this oxide film, not the aluminum. And this way they can do kind of a new etching of aluminum surface and create these wonderful surfaces which are energetic-wise extremely repellent. These coatings are not that seldom to make something ultra-hydrophilic. It will also work This is conventional cardboard, which somebody brought as a note, my secretary probably, to my office. And now the other surface is coated just with some silicone type of polymer. We have the roughness from the cardboard and the silicone, and now this is also ultra hydrophobic. So you can see that here. If I don't know, can you see this from the back? At the middle here, it's not kind of wetted in any case, but that the whole thing is ultra hydrophobic. Yeah, maybe you can also pass it around. Be careful, the tendency is that it rolls off. Yeah. Okay. Yeah. So these artificial hydrophobic materials are quite quite state of the art now, I would say. This is new. This is unpublished stuff, but I was thinking it could be interesting to show you what is going on, that you can now also convert metals into this ultra hydrophobic materials. Yeah. By the way, these structures are not designed for that. They are designed for adhesion, but maybe this is going too far. So better I go back to biomedical topics. And now I wanted to start to tell you something about drug delivery, where you also need this wettability concepts. But then I have to ask you, how much time do I have?
Well, please continue. How much time you need?
I will need the time you give me.
Well, 15 minutes.
15 minutes, okay, that's fine. Yeah. Also in the body it's quite important to know about hydrophobicity and hydrophilicity. Switching topics, drug delivery. Yeah. 75 to 80% of the new discovered drugs, so this type of chemistry, is hydrophobic material. And typically, in order to get something into the body, you're grinding it and so on, so you have a rough surface. So imagine what happens, the whole stuff is ultra hydrophobic. So it's very bad to get this into the body, which is basically hydrophilic and basically equipped with water. So we have to do something about that. And there's other tricky things if you want to administer a drug. It could be hydrophobic, this could be one problem. The other thing is that first you have to get it into the body. So there's a kind of cell barriers, there's epithelia and endothelia barriers. So if you have something like a pill, you get in, it must go somewhere to your digestion system in order to penetrate the body. Or if you make it kind of brutal, then you do an injection through the skin in order to get it somewhere distributed in the body via, for example, blood vessels and so on. So if you have an effect, then you have like a target compartment which you want to reach. On the other hand, you have some part, some kind of unwanted place where it could go as well. For example, if you think of an aspirin, typically it's against headache after, caused by whatever, and but the aspirin is kind of going through the whole body, not only at the brain where it should have its effect, for example, as a painkiller. This aspirin has a kind of side effect, it's diluting the blood, so if you get injured, it will take a longer time till it's healing. So these are the problems with drug administration. And as this lecture should be somewhere at the edge of nanotechnology, I was looking for a concept where one is using nanotechnology and drug administration. And there is some work which is discussed in this publication here from an American group, and they are using the so-called enhanced permeability and retention effect, EPR effect. And what has this to do with nanotechnology? Think of, it's a serious problem. There's some person who has cancer. If you're taking a look at the tumor site, then you will see that it's kind of growing and growing tissue. So cells are dividing themselves in an uncontrolled manner. This is growing further and further, and at the end even killing the person. These cells might spread, and these cells are not working right. Otherwise, the cells would kill themselves, so there's a protection in the body to avoid this. And in cancer, this protection is kind of out of control, and it gives you a lot of mutations of these cells, which are more and more dangerous and not working right. But that they're not working right is also some advantage where we can make a targeted drug delivery if we overcome the hydrophobicity problem and if we employ nanotechnology. This is shown here in this schematic. Think of this would be tumor tissue, and this would be a part of a blood vessel. Then you have here this endothelial cells, which are typically sealing the other tissue. So those cells here are typically a barrier against everything which you see in the blood cycle. So if there would be some small molecules or nanoparticles or something, they typically could not penetrate. If they still would penetrate here, then there would be a lymphatic system, a lymph capillary, which is removing this at the normal tissue. At the cancer site, you have cancer cells, and cancer cells are not working right. So this barrier is not intact anymore. It's fenestrated, so you have some tiny openings which allows you, if there are, for example, nanoparticles, to go inside the tumor site. And also the lymphatic system is not working very well. And there were some clever guys shown here, which published and experimented with this kind of nanoscale particle, which is now combining all kinds of concepts in a clever manner. Inside is a more or less hydrophobic drug, which is able to kill cells. Typically, you don't want to have this drug messing around in the body because you want to stay with your cells. In chemotherapy, you typically put this kind of toxic materials to the body. In this case, those are inside of a shell. This is here like a lipid membrane, phospholipid bilayer, and this lipid membrane is equipped with polyethylene glycol at the outside. Polyethylene glycol is a hydrophilic material. So it's included here into this kind of shuttle inside and is now well adapted by the blood cycle. And if it's cycling around and it finds these openings, then it goes to the tumor site. And sooner or later, this shuttle will break, and then it gives away this cytotoxic poison right at the site where it should go. So, question remains how to build, how to construct this type of shuttle. Well, nature is doing it basically. This is how cell barriers work. Typically, this barrier is done from some molecules, which are some bilayers. They have a hydrophobic and hydrophilic compartment. So they have a hydrophilic head and hydrophobic tails. So this hydrophilic head will arrange always to water, while this hydrophobic tails will kind of arrange next to each other. It's shown here. And this gives you a typical barrier which you have somewhere on the surface of the liquid. If you're inside of the liquid, it forms a double barrier. You have liquid from both sides, and this is hydrophobic. So, and it's not easy to penetrate through this barrier, which with anything which can be dissolved. And this is this trick how to enclose material inside of these shells. So these can move slightly against each other. For example, a bacteria is using this trick. So this is kind of combining both of those. This has a larger scale. So one is again stealing these concepts from nature in order to employ them, here in this case for drug delivery. However, final topic, as I have to hurry up, now more for the electrical engineers, I want to talk about zinc oxide. Zinc oxide is known as a wide bandgap semiconductor and has firsthand nothing to do with and nothing to do with medicine. It's only treated as a biomaterial. Maybe those of you who had problems with some skin, they find that zinc oxide is also used in some creams where it has a certain medical use. not only as a wide bandgap semiconductor. But those from who are from electrical engineering, you could see these are transparent hexagonal crystals with a bandgap of 3.37 electron volts. This is a nice material we use in our group because it's very easy to form nanostructures. This has something to do with the polarity of these crystals. Like water, zinc oxide is very polar, and so therefore, if you're doing some growth process, typically inside of the crystal it shoots up in one direction. This direction is the versite crystal system, so it's the O1 direction, the C-axis, where it grows very fast, and these other sides are growing very slowly. And just if you take a zinc grain and oxidize it, more or less in a clever manner, you can put here some gold nanodots, for example, you have some growth of some little spikes which are going off. And these are still single crystal. And one funny effect is, which has to do something with the size, nanoscale is different, that those ones are curving around here. Why is that? Well, it's like an extreme glass fiber. If you have a glass, window glass, you cannot bend it. If as a child you've hit it hard with a soccer ball, for example, it will break apart. A glass fiber is not doing it, it's bending it. Why? Because it's simply thinner, there's not so much force at the inside and outside, so you can bend it. If you make this glass fiber nanoscale, then you can bend it really heavily, no problem. So this inspired us to say, oh, can we use this stuff in order to build a kind of flexible ceramic material, where we have here this little kind of flexible legs employed in a kind of bulk material that you can really take in your hands. So like this, you build a core shell particle or core spike particle, where you have a lot of spikes on a core, and now you make a material where only these spikes are interpenetrating. And in PowerPoint this was running immediately quite well. So if you compress the material, you see it's deformable, almost elastic, so that works. But we wanted to do it in reality, so we built a very simple process to oxidize our zinc in a very simple oven. We took these zinc particles and had a sacrificial polymer which was just burned. And now you're converting this to zinc oxide. The spikes grow at the same time and penetrate. But it's not one mass, it's not like one zinc oxide block, but the whole thing is kind of nice and has a lot of free volume. And this was the result of these first experiments. You can see a lot of spiky material, and indeed only these spikes are interpenetrating. But this was a problem because this was only useful as surface coating. So we went one step further and we observed the same accident like you have seen if your pizza is too long in the oven and you're opening it, exposing it to oxygen, it will be immediately oxidized. And then some vapor is coming up, and this is containing particles. You can do the same with your oven. You have your zinc particles, and now we call this flame transport synthesis because you're using this flame, the stream up, where freely now the zinc can be oxidized, and it can grow in all crystal directions like it wants, and it can be done in a very fast manner. So these are separated in the upstream, and now they can be sintered here at the catcher substrate. This is how it looks in reality, and this is how it looks after the synthesis. So you see you get a white powdery substance looking basically like ice, because they're also very polar molecule and transparent originally, but nanostructured. And you can see this here. You can even grow larger crystals here at the top and smaller crystals inside. And now we are scaling this up because this material is technical use, so your whole oven is kind of full of this white fluffy powder. How does it look? Like you want, basically. Most important variety for us is this one, where you have this kind of chains of tetrapods. This is a tetrapod. A tetrapod is a clever material structure, because if you push the tetrapod on the head, it puts all its weight here on these three arms. And if the tetrapod is now connected with another tetrapod, the same thing happens. So all the forces are kind of distributed quite nicely. And if these arms are quite thin, then you can bend them. So then you are on your way with a flexible material. And somehow I stopped the presentation. Okay. So you can make all varieties of these tetrapods of a hair, a metal wire, and this is here this tetrapodal network. And if you push on that one, then you see it's like breathing, it's flexible, so it's not doing kind of any breakage. And I was bringing some of this material to you. This is here done even from the company, by the way, Ala is working now, and they are producing this material, and all this material is kind of this wool type of tetrapod material. So this is here full of tetrapods and out of zinc oxide. So you could think I'm doing a fake now. This is not a flexible ceramic. It's marshmallow or something where you put your powder on your skin. But I can prove that it's ceramics. This is here kitchen equipment. This is for converting sugar into some molten state for dessert, and so very delicious. So this has quite some flame, as you see here. I make it larger, then it's more effective. So if this would be organic material, it would immediately burn this material, but this material is not burned because it's ceramic. Zinc oxide is a ceramic, and my hand is also not burned. And you see it's kind of glowing, it's getting yellow. This has to do something with the surface oxygen vacancies. Now it's yellow, I don't know if you can see it, now it's white again. So some oxygen is going away from the zinc oxide, oxygen vacancies, and now it's away again. Now I can make it again a little bit hot. Oh yeah, maybe that's a good idea. Can make it again hot. And now I can immediately touch it. You shouldn't do this with a metal. You can only do it with this material because it's out of the tetrapods, and all the tetrapods are surrounded by air. So this material has like 95% porosity. So there's almost nothing inside except this little ceramic networks, and so therefore it has a very low heat capacity. On the other hand, I'm holding it in my hand. On the other hand, I'm holding it in my hand anyway. I can hold it in the hand as a kind of fire protection. So this is not a biomedical application, but maybe a useful application as fire protection. So if I have a glove for that, so for the next conference I bring a glove out of it, I could directly go inside the flame. The melting point of zinc oxide would be 1950 degrees. So no chance to get this molten here with these 1000 degrees, and it's quite cold, and it's really fluffy material. And yeah, now we can maybe expose it again, and if I have deposited carbon now on top, maybe we can switch on the light again. Possible. Then the whole thing should be ultra hydrophobic because I have done a deposition of a thin carbon layer. And this graphite is typically hydrophobic. If it's still zinc oxide, it's hydrophilic. So actually I don't know which. It's either ultra-hydrophobic or ultra-hydrophilic. So if there's a droplet staying, then it's ultra-hydrophobic. And you see it's no droplet staying. It directly soaks in the water. I don't know if you can see this, but the water goes directly in and nothing's going to happen. Actually, it looks like it's going a little bit more tiny. Why is that? Well, we talked about capillary force. So the zinc oxide is a very polar material. If it's unprotected to water, the water really likes it. And it likes now to compress the material inside, so it takes these capillaries together and is grabbing kind of the arms and is bending all these tetrapods. And now it's, yeah, feeling a little bit like a kitchen sponge or something like that. Yeah. Bit messy, I don't know. Later on, if somebody wants to see that, we can play around with this. Okay, then I'm almost completely finished. Coming back to biomedical use of this material. Where does this should be useful for biomedical? Well, one thing is it has a lot of openings, so one can grow cells in it and so on, all this biotemplate business. But we found, surprisingly, something funny. There was a guy from the US, originally from India, but he was going there, and he was saying, you have nanomaterials interact with viruses, give me some material. And I said, oh, stop, how should it work? I had no clue about viruses, and I said, yeah, is your virus polar? And he said, yes, it has some attraction somehow to polar surfaces. Okay, then I give it a try, and I gave him some of this zinc oxide. And in order to understand what's happening, we have to understand a little bit what a virus is and what it does. So typically viruses are these little things which are entering cells. And these are doing it with a tricky manner. The cell has this kind of barrier out of this lipid bilayer thing, as you have seen. So typically it cannot pass it. So it's doing it in a tricky manner, as you see here. So this is here this viral particle. This is the surface of the cell. This viral particle is equipped with some glucoprotein groups. These ones are fitting quite nicely to some functional groups which are sticking out of a cell. And now it's going close to the cell, and as the whole thing is nicely at body temperature, then there's some kind of connection between these membranes, and at some point the whole thing fuses. This goes into the kind of full membrane, and what's inside of this viral particle goes down. A virus actually is only this program code. It's a sequence of RNA and DNA, and if it makes kind of your cells in the body to read it, it has a construction how to replicate itself and send it off. Not by email, but just in the body with the cells. So it works exactly like an electronic virus. Actually, this virus concept was there before, but nowadays it's easier for us to understand, especially if we're from electrical engineering, how it works. So think of a computer virus. This is a biological version. You have here some program code. If this gets read by a cell, the cell is forced to replicate it and builds kind of this whole shell and this whole particle together and sends it through the body. And then you have a problem because it's doing thousands of it. So who's interested in that, finds this reviews quite helpful, because also somebody who's not inside can understand something. And this is what is explained in there. This viral particle get into the cell, doing here some things which biologists know, but it's replicating itself, and thousands of viruses are coming off, and then they are kind of exiting. So the cell is typically dead then, and they are kind of now on the run on a lot of other cells. If this is the HSV1, so which is a herpes simplex virus, then you have a problem, for example, on your lips, like this one, because these are kind of these cells which are fused and abused, and where all this production was in, so get some blistering. And there's some more problems with this virus, especially there's a genital variant which is not so harmless and is a big problem worldwide in terms of disease. So what can zinc oxide do against this? Well, this was a surprising thing. It works like this trap for insects. So basically the virus glues to the surface of the zinc oxide. How that? This is a zinc oxide crystal structure, and this is an oxygen vacancy. And these glucoprotein groups, which are outside of the virus, this is not to scale, only for illustration, they fit nicely into this oxygen vacancy. This was a very good luck, because now the virus is gluing here on the surface and is inactive. It likes the surface very much with electrostatic, but it's not, it cannot do what it usually wants to do, like attacking a cell. So there are people who understand things about this, these guys in America. We have now a long-term collaboration. We are sending off all variants of our zinc oxide material, and they're testing it with all kinds of viruses and cells and so on. And they could show then some experiments even I could understand. So what they're doing is they're making a control experiment. What you see here is a fluorescent signal which is measured. It shows the cell entry, so how much viruses go inside of a cell. If you're doing nothing, you have a certain quantity what goes in. If you put at the side of the cells some of the zinc oxide, for example, like this network, or like nanoparticles like this called spike particles, then you have a much reduced entry of the cells. And then what is very funny, in order to confirm the theory that it has really to do something with these oxygen vacancies, I told them expose the zinc oxide before you do the experiment to UV light. Then the same is happening like what was happening with the burner. Oxygen vacancies are created. They take some time till they're reduced, and if you do this illumination before, you're increasing the effect drastically. For me, this was a strong hint on this mechanism that these oxygen vacancies, which you would say as electrical engineer, hey, these are doping sites, they bind this virus on their surface, and now this stuff is immobilized. And now there are manifold applications. It's not only working with zinc oxide, but also with tin dioxide. You can do similar things. But if you would tell somebody, especially from pharmacy, hey, I have here some crystals, and if you shine light to them, for example, put them to sunlight, before you're doing your experiments, they are more efficient, they throw you immediately out as some guy who's not quite right. But with this explanation, it's probably less mystic and somehow in the interface between, let's say, surface science and biology. There's one aspect one always has to deal with, and this is the last slide. This is, one always has to make sure that the stuff one is utilizing, like the semiconductor material, is not killing you. It should kill the virus, but not you. So you must check the cytotoxicity. So we are working here with the toxicology department and made a lot of studies about how biocompatible this zinc oxide stuff is. And it turns out it's very biocompatible. In order to hinder cells on kind of growing, you need a lot of concentrations. This is always important in toxicology because everything is toxic. It just depends on the amount of material. If you think of sodium chloride, we all need sodium chloride for our body to function, but if it's overdose, you have a problem. It's too much salt. If it's too less, then you die also. So the dose is always the effect. And here you see in cell cultures it behaves very well. So this is only what you have to make sure. So summary, I could say there's a lot of things to discover at the interface between nano, biomedicine and materials, I would say. Maybe this could be a conclusion. I want to thank, of course, the team who did all these experiments and comes up with these beautiful ideas how to abuse, for example, semiconductor materials, and some funding agencies. There's some funding provided from the country Schleswig-Holstein, which is very north in Germany, and for a German country, very poor, so we also have to get money from the German Science Foundation, from EU and everywhere else. So thank you very much for staying awake so long, and if you have questions, I'm of course happy to answer them, otherwise I'm not in the way.
If we use oleophobic surface of water, so it will be the same like hydrophobic and hydrophilic. So it will be reflection of the water the same, will be if we use oleophobic.
Oleophobic?
Yes.
Yeah, it is this kind of phobic surfaces can be tuned. I was only talking about polar surfaces, but there are some surfaces which are incompatible with oil, and there can be now a variety. You can also create an oleophobic surface which is hydrophilic. So this could be a very nice membrane, for example, to separate oil and water, which can be a problem.
Because now some of these oleophobic technologies using in mobile, like Sony Mobile, using like oleophobic to put in, because their devices now are water resistant, and to wash the water or dust resistance, we put oleophobic to wash all the dust or influences from the devices. So,
yeah, for example, for environmental protection, there's these ideas. For example, coming off with, you could take this three-dimensional network like the zinc oxide, and you can coat it with carbon. We've done it and etched away the zinc oxide. Then you have something which is hydrophobic, but oleophilic. So this would do the trick, also soaking up oil from water surfaces. This is at the moment discussed. All this depends on how good is the mass production of your material. It doesn't help you if you can only make kind of the tip of the the fingertip, so to say. This is why we struggle in our lab with these very simple oven techniques in order to, that I can have here a box and show around and be proud that I have so much nanomaterial. Yeah.
Thanks very much.
Some other questions, please? No questions, then thank you once again.